adding vectors is an important thing to do, important to be comfortable with, especially now that we're thinking about forces and net forces. We need to be able to add force vectors together in order to find a net force. That's what you need in order to find an acceleration. So you start by imagining over here three vectors, and just to keep things a little bit simple and more concrete, let's think of them as three displacement vectors. So there's some kind of a motion that started here and ended here. Anything could have happened in between the start and the finish, but the net result of that motion was that you moved from here to here. And then imagine immediately after doing displacement A, you do displacement B, which would take you from your starting point to a point that's this far away. And then immediately after doing displacement B, you would do displacement C. And in displacement C, that takes you from your starting point to a point that's this far away in this direction. So now imagine doing displacement A, then doing B, then doing C right after the other. And we'll imagine a coordinate system where the very beginning of this series of displacements is right here at the coordinate axis. So first, you do displacement A, and then when you have finished displacement A, you're right here at the point that's indicated by the tip of arrow A. But that point is also the starting point for displacement B. Right after you finish A, you're going to do displacement B. Right? This tip of A is also the tail of B, because this point is both the end point for displacement A and the starting point for displacement B. So the A and B are then connected tail to tip. Then you do displacement B, which takes you from this point to here. This is the final location for displacement B, but it's also the initial location for displacement C. So tip of arrow B, that means it's the final location for displacement B. This point is also the tail of displacement C. That means it's the initial point for displacement C. Because you do displacement C immediately after you do displacement B, you connect the tail of C to the tip of B. Because the start of displacement C, the tail of C, is right where you finished displacement B, the tip of B. And that's that tail to tip connection, right? The end of one displacement, a tip, becomes the start, the tail of the next displacement. That tail to tip connection is something that we do when we're illustrating any addition of vectors, not just displacements. It's just a little easier to understand why the tail to tip thing makes sense if we're talking about displacement vectors. Because in displacements, it's a movement from here to here to here to here. And then the net result of that movement was a change in location from here, right? The starting point of the first displacement, the starting point of A, to here, the final location of the last displacement, right? The final location of displacement C. So the sum of displacement A plus displacement B plus displacement C, the sum of those displacements, that is the net displacement, is a movement from here, the very beginning of the path, of the ABC path, to here, the very end of the ABC path. And that's a pattern that we see always in all illustrations, in all of these arrow pictures that illustrate the addition of vectors. The things being added are connected tail to tip, like A, B, and C in this case. And then the arrow that represents the sum the net displacement D in this case. The arrow that represents the sum is an arrow that goes directly from the very start of the path directly to the end of the path. The other important point to notice in this diagram, imagine now each of those displacements, A, B, and C, and think about their components. Remember that the relationship between a vector and its components is just like the relationship between the hypotenuse of a right triangle and the two perpendicular sides. So here's the triangle that represents displacement A and its components. Here's the x component of A, some displacement, this much displacement along the positive x direction, and then here's the y component of A. And then here's the triangle that represents B and its components, and here's the x component of B, and here's the y component of B. X component of B, y component of B. And B itself can be thought of as a sum of this much motion in the x direction plus this much motion in the y direction. And likewise, here's the triangle that represents C and its components. Here's the x component of C. Here's the y component of C. Now, this length is the x component of A, and then this length is the x component of B, and then this length is the x component of C. But add the x component of A to the x component of B to the x component of C, and all of this is simply the x component of D. Imagine the triangle that represents D, the net displacement, and its components. Here's D, the hypotenuse of that triangle, and here's the y component, and here's the x component. X component of D, y component of D, D. So this is the x component of D, but it's simply the sum of AX plus BX plus CX. And algebraically, I've written that here. The x component of the sum, the net displacement, is just the sum of the x component of A plus the x component of B plus the x component of C, and the same thing is true for y components. This much distance is the y component of A. This much distance is the y component of B. Here's the x component of B, here's the y component of B. And then all this distance is the y component of C. Here's the y component of C, and it's just equal to that distance. But the y component of A plus the y component of B plus the y component of C is just the y component of D. This distance here, which is just the sum of AY plus BY plus CY, this distance here is the same as this distance here, and this distance here is just the y component of D. This is just the vertical perpendicular side of the triangle that has net displacement D for its hypotenuse. So the y component of the sum vector is just the sum of the y components of the vectors that are being summed. Or to put it in a simple terms, like I've got right up here, the x and y components of a sum are simply the sum of the x and y components of the vectors that you're adding together. Now look at a bit more specific example of that. three more displacement vectors. I'll call them A and B and C again, but they're different vectors from what they were this time. Here's vector A, which points up and to the right, and it has an x component of positive 10 meters and a y component of positive 9. And then here's vector B, which has an x component of negative 3 meters. Right? The displacement along the x direction is in the negative direction of 3 meters long, and then the y component of B is positive 1 meter. And then here's vector C with an x component of minus 3 meters and a y component of plus 3 meters. So if we were to draw the picture that shows how A and B and C are added together and what kind of a net displacement you get out of that, the picture would look something like this. So here's A, and then B, A and B are being added, so we put the tip of one at the tail of the next. Since they're displacements, this is the final location when you're finished with displacement A, but then this point here then becomes the initial location for displacement B. And an initial location of a displacement is represented by the tail of the displacement arrow. Then at the end of displacement B, you're right here, and at that point you go through displacement C. But here, the final location of displacement B becomes the initial location of displacement C. Like that. And so the net displacement took us from a starting point here to a finishing point here. So the net displacement, the grand total displacement, is a displacement from here to there. D, the arrow that represents the net displacement vector, like all net vector arrows, goes directly from the start of the path, not along the path, but directly to the end of the path. Okay, now let's use this principle, component of a sum equals sum of the components. The x component of D is just the sum of the x components of A and B and C. So x component of A is 10 meters. X component of B is minus 3 meters. And the x component of C is minus 3 meters. So the x component of D, turns out to be 4 meters. That is, if we imagine the triangle that has D for its hypotenuse and the x and y components of D for the other sides, that triangle would look like this. And the x component of D would be that. And it has a magnitude of 4 meters. And now the same for the y component of D. The y component of the sum equals the sum of the y components. So the y component of A is 9 meters. And then the y component of B is 1 meter. And then the y component of C is 3 meters. So the y component of D is plus 13 meters. And here's the y component of D right there. 13 meters. In other words, another way of getting from this point to this point, well, one way of getting from this point to this point would be to take the path A plus B plus C. Another way of getting from this point to this point would be to go 4 meters along the positive x direction and then 13 meters along the positive y direction. Or a third way to get from here to here is just go directly along displacement D, the sum of displacements A and B and C. Okay, well now we know that the x and y components of that sum vector, so we can actually figure out two things about that sum vector. We can figure out the magnitude of that total displacement D. The magnitude of any displacement vector is just the distance between the start and the finish, and that of course corresponds to the length of this hypotenuse on this right triangle, and the length of the hypotenuse is just length of the hypotenuse, which corresponds to the magnitude of D, is just square root of the sum of the squares of the other two lengths. So the magnitude of dx squared plus the magnitude of dy squared, and take the square root of all that, and that's the magnitude of the net displacement vector D. And in this case, that's what? Dx was 4, so dx squared is 16 square meters, and then dy is 13, so 13 squared is 169 square meters. So this comes out to 185 square meters. Square root of 185 square meters is about 13.6, rounded to 14 meters. So it's about 14 meters from this point to this point. And in order to get from this point to this point, in what direction do you have to move those 14 meters? In other words, what's the direction angle for that vector D? We figured out the magnitude of D. Now we need to figure out the direction for D by calculating the direction angle. And of course, like you did in class the other day, it's a matter of using tangent. We'll take that for our direction angle, and that means that tangent of that angle is a ratio of the side opposite over the side adjacent. Side opposite is 13 meters, side adjacent is 4 meters. So we're looking for this number, that is the number that has 13/4 for its tangent. In other words, the inverse tangent of 13/4 is the angle that we're looking for, and that comes out to, let's see, about 73 degrees. And specifically, 73 degrees counterclockwise with respect to the positive x direction. If we initially point in the positive x direction, then rotate 73 degrees counterclockwise, we will now be pointing in the direction of the net displacement D. So just for completeness here, I want to say this is 73 degrees counterclockwise with respect to the plus x axis, positive x axis. Okay, now that sort of thing is the thing we'll be doing quite a lot when, be thinking about that quite a lot when we are thinking about adding forces in order to get a net force. We do the same kinds of things as we did here, except just imagine that instead of all those vectors we were adding together, instead of them being displacement vectors, now they're force vectors. But everything else in the thinking here, everything else in the process is just the same. So that's the end of this part 1 video. Going to part 2, we'll look in a little more depth at what you can actually do with Newton's second law, how you can actually use it to understand various physical situations.